Hi everyone, so today we will conclude our lectures on foliation and lineation. So to start with, first let us see what we have learned in our previous classes. So we have already learned what is foliation, and foliation, we know that it is a planar parallel fabric of the rock, and in foliation we have learned about cleavage and what are different types of cleavage, and also the relationship of cleavage and strain. And after that we have come to what is called a layering, and how this layering is seen in phyllite, schist and gneiss. So now that we have understood what is foliation, so today we will briefly discuss what is lineation. We know that lineations are linear and parallel arrangements of fabrics in a rock. We have also discussed that if a rock has a linear fabric, that then it tends to break into small rods. And so we'll see some examples of lineations today. And after that, we will come to the relationship of this foliation lineation to tectonics. So this is going to be like lecture on the practical implication of the foliation lineation, like how we see this in field and what kind of implications we can make by seeing identifying these features in the field. Just to give you some example of lineation, lineations are linear features. So how these lineations are formed, like we have seen that when the folding of the foliation planes occur, so there can be some kind of secondary uh, kind of foliations formed in the rock. When the foliation planes intersect with the original foliation planes, then we can see some intersections in the form of lines, because when two planes intersect they form a line. So here the this gray plane, this is a foliation plane. So when this plane it got folded, so some secondary foliation plane may develop along the hinges of these folds, and this may lead to development of some lines along these hinges. So this is what we have also discussed in granulation cleavage, like we have symmetric granulation, asymmetric granulation. So there we can have this kind of lineations in the hinge of the folds. Similarly, if we have a sandstone and a shale bed, then the competent sand, they can form some depression into the shale, because shale is incompetent, that is weak, and sand, if it is sitting over the shale, it can just deeper into the shale. And in the crest of this region we see some narrow crest, and the trough will be broad. So this kind of contact between sandstone and shale leads to formation of these structures which are called mullions. Similarly, when the folding occurs between a competent and an incompetent rock, then the competent rock may tend to break, because the competent rocks are hard, they cannot extend easily like the incompetent rock which is soft and they can extend. This forms what is called the budins, and due to these budins, in the neck of budins we can see some lines. So these are also called lineations. So these are different examples of lineations. Like that we can see that suppose we have a bedding, and after the bedding we have some foliations due to arrangement of the phyllosilicates, like the mica. So when these foliations, say S1 foliations, intersects with the bedding, they also tend to form some intersection. So these are called intersection lineation. These are called bedding foliation, S0 S1 intersection lineations. So like that, intersection lineations are seen in this figure due to the intersection of the foliations which are developed due to the folding here, and the bedding. These beddings we can see by from these alternate layers, and the S1 intersection lineations can be seen in this plane here. And similarly, if we go to the falls, so there in the falls we see that one block will move down. If this is the fault plane and this is the deep direction of the fault, then the block which is sitting over the fault plane, that is the block which is towards the deep direction, this is the hanging wall block. When this hanging wall block moves down, then we can see that there are some thin line kind of things which are formed on this fault plane, and these are also called slicken sides. These slicken sides are also lineations, because they are linear fabrics formed on this wall. And sometimes we can see that there are some mineralizations which can grow in this like we can see here some calcite or some kind of minerals may grow in this veins. So this also may leads to formation of some linear structures, and these are also called mineral lineations. Similarly, in this line we can see some quartz veins, and this also moves like a line in this rock, that also may be called the lineations. This way we can see that lineations can be formed by a number of ways. They simply represent some linear fabrics in the rock. They are in the form of straight lines or carved lines. Okay, now we have understood what is foliation, and we have also understood what is lineation, and we have also seen different kinds of foliations and lineations. Now what we will see is that we find this foliation lineation in different kind of deformed rocks, and what kind of interpretation we can make in field from this kind of rock. So first let us go to the relationship of foliation lineation to shear zones. Before going to this topic, let us first see what is a shear zone. So actually shear, we know that when there is a tangential force acting on a plane, then that will lead to a shear. Suppose we consider a plane, this particular plane here. So we have a tangential force, say one force is in the downward direction in the topmost block here, and the other force is in the upward direction in the bottom block here. Now near to the surface we have low pressure temperature. In this low pressure temperature, generally brittle deformations are seen. So here we will see that more faulting will occur. As we go deeper, this zone converts into ductile zone. In ductile zone we do not see much brittle deformation, rather we see plastic deformations. So that includes plastic deformations like folds. So as we go into higher pressure temperature environment, the rocks do not break, they simply get folded, or they simply start moving in a plastic deformed way. So in the deeper part we get what is called the ductile shear zone. So here the rock may show displacement, but there will not be a brittle failure. So rock will not break along any surface, but slowly that rock will tend to move, and they will show displacement. Like we can see that this particular layer here, it has got displaced to much deeper layer, but there is no breakage in this layer, this bottom layer. So although this is displaced, there is no breakage. Now from here we can see that in the top part of this ductile shear zone, this is much thinner than the bottom part. So this shear zone, they spread in a wider region as we go below to a high pressure temperature region. So this shear zone will slowly start, say at this particular depth, and as it goes below, a number of shears will form from here, and finally in the bottom we will get a wider zone of shear, which is called an anastomosed shear zone. So this is a particular say characteristics of a shear zone. What is to be noted here is that a shear zone represents a zone where there will be movement of blocks. The movement will not have any complete breaking of the rock, but there will be movement due to high movement of adjacent layers in a plastic formation. That means layer by layer the rock will be moving each other, and finally the rock will have displacement adjacent to the shear zone. Now in this shear zone we find a specific kind of rock which are called myelonites. So myelonites are, since they are related to shear zones, they are ductilely deformed rock. There is no brittle deformation in myelonites. So they will show displacement, but there will not be a chain of breakage. The rock is not broken, but there is layer by layer movements, and they are formed due to large shear strain. So like we have seen in the previous slide, there is a very large shear along this zone, that is extending from almost upper surface to the middle of the crust, and that kind of strong shear is leading to the formation of the myelonite kinds of rock. Now, what are the characteristics of myelonites? So they are ordinarily fine grained, because due to shear, the grains here gets recrystallized. Like we have seen previously that when we are discussing metamorphism, that due to high pressure temperature, some minerals are getting unstable and they are forming new minerals. Like that in myelinite also, due to compaction, as resulted from the shear, the rock is getting recrystallized into finer grains, and this results in a reduction of the grain size of the rock, and these myelonites are therefore classified as metamorphic rocks. They are also formed in high pressure temperature environment, more specifically in the high pressure environment. That's why they are called a result of dynamic metamorphism. Dynamic means they are mostly affected by the pressure. Now, how this myelinite originate is a very difficult topic, and there are many views on this. But in general, it is believed that they are formed due to crystal plastic deformation. So, what is this crystal plastic deformation? We have already learned that due to instability in the mineral phases, as the pressure increases, new crystal will form. So, there will be recrystallization, and there will be flowage of minerals. Like in case of folds, we see that the rock gets deformed into bands. Like that here also we get that the rock will be deformed in bands, which will be called plastic deformations. So plastic means they will not come back to their original shape, so their shape will be changed. Like in this third figure, you can see in a ductile shear zone how the shearing is occurring. This top and bottom arrows, they show the shearing, and due to the shearing, this block has moved, this left hand side has moved up and the bottom side has moved down. So in ductile shear zone, we do not have any breakage in the rocks. This yellow region which represents the shear zone, this shows how the rock is getting plastic deformation here, and there will be recrystallization also due to high compaction. So this is a crystal plastic deformation, and in the secondary phase there may be some kind of fracturing, and there will be cataclastic flow also in this myelinite. So if there is a brittle ductile shear zone, then there we will see some brittle deformation also. So some faulting is also associated with these folds. This yellow colored region is the shear zone, where we can see this blue line. This blue line is a straight line. If it is a brittle shear, it will simply get displaced along the fault plane. But if it is a brittle ductile shear zone, then there will be breakage, as well as there will be minor folding in this region. So you can see that the blue line here is getting folded, as well as it is getting displaced. And in the ductile shear zone, we see that the blue line is continuous. There is no breakage in the blue line, so there is no brittle deformation here. But this has gone plastic deformation, so there is a folding here, but there is no faulting here. And it was initially believed that these myelonites were formed because of the milling of the rock. Milling means we have crushed the rock, but later it was seen that there is no milling associated with the myelonite, although this term was originally coming from the Greek term mill. Now we will see how these myelonites actually look in a field. So this is a typical shape of a myelonite rock. Myelonite can have a wide variety of mineral composition. They may be formed from different kinds of rocks. Myelonite is having some specific textures. So this kind of rocks are basically named because of their textural elements, not because of the chemical compositions. So, and here we can see that the phyllosilicates, due to high pressure, they will get arranged into some foliations. So we'll have these foliation planes which are very compact here, so like continuous cleavage, and in between we have some remnant crystal, as you can see here, and these remnant crystals are called porphyroclast, and they have thin tails. If we see this crystal, adjacent to crystal, we have some thin tails on both sides, and these are formed due to recrystallization of the edges of this crystal. So due to high pressure, this crystal is also getting recrystallized in these edges, but the central portion of the crystal is still intact. So these are called porphyroclast, and we have small white feldspar porphyroclast also. So so this shows how a myelinite actually looked in the field. And now we have understood that what is a shear zone and what is a myelinite. Now we will see what is the implication of this foliations in myelinite in the shear zone. We have seen that suppose this is the surface of the art, so in the top part of the crust we have mostly brittle deformations where we see the falls, and after that as we go below we can see that we reach the myelinite zone. In this zone we have either brittle ductile deformation or complete ductile deformation, and as we keep going to higher pressure temperature region, as the degree of ductile deformation increases, in the bottom part we get the niches, so there will be complete recrystallization of the rock, and then rock will form the layering, and it will completely wipe out its previous foliations and all, then it will convert into niche. So we have already learned how it occurs. So before that, in the initial phases of deformation, as the pressure increases, we see this myelinite zone is seen. When we talk about the myelinite zone, so we have a shear stress associated with it. So suppose we take this block and we have a shear stress. So shear stress will be acting parallel to the plane. We know that this is a tangential stress. So due to this stress, suppose there is a brittle ductile deformation. So because of the brittle ductile deformation, the rock got broken along this fault plane, and there is some bending of the minerals also due to the ductile deformation. So these are the plastic deformation. Now this has led to the development of some load strain lengths in the rock. Now if we take a segment parallel to this lineation, if we cut a segment parallel to this lineation, a vertical segment in the rock, then we can see that in that we will see this foliation and lineation like we have seen in our previous figure. In this particular figure, like we have seen these foliations, and so if we take that section parallel to this lineation, then we can get the foliations the of the laminate porphyroclast. This particular porphyroclast which we see, they have some tail regions also like we have seen, and this tail region of the porphyroclast, they can easily give us the sense of shear. What does the sense of shear means? Whether the shear is dextral or sinistral. That is very important for us, right? Because this will give us the entire deformation. If there is a dextral shear, this top arrow is moving in the right hand side. If we are standing here and if we see this arrow, it is moving in the right hand side. Similarly, if we stand here and see this arrow, this also will move in the right hand side. So this is the dextral shear. So if suppose we are standing in some places in Himalaya and we see this kind of dextral shear, then we come to know that what kind of deformation is occurring in this whole region. So basically the whole importance of this foliation and lineations comes from this fact that if we cut a section along this lineation, we can find a sense of shear in the whole region. So these minute structures, these are like very small scale structure, less than the size of a coin also, like we have seen in the previous figure. So this can give the whole deformation which is taking place in the entire region. This is the practical significance of foliation. If we go to the field, if we find out the small lines, their orientation, we can find out what deformation is going on in the whole region. So let's see in little more details how we find out these deformations from this foliation and lineation. Suppose we have this rock and we have some shearing occurring along this rock. So due to shearing, if we see this rock, we can very easily understand that the bottom part has moved towards left and the top part has moved towards right. So we can see the sense of the shear. If we stand in this portion, in this shear zone, we can see that this part is moving towards right of us and this part is also moving towards right of us. So this is a dextral shear zone. So if we see this shear zone, we have three planes here. So this particular plane along which the shearing is occurring, this plane along the x, this is the shear plane, and the plane which is perpendicular to it, this is the displacement plane. So we can see that the displacement has occurred along this plane, this vertical plane. So in the shear plane we do not have displacement, vertical to it we have the displacement along. This is the direction, the plane which is along which the shearing has occurred is the shear plane, The plane perpendicular is the displacement plane, and the direction of shear is towards this side, so towards A in this figure. Now if we see the strain ellipsoids here, the strain ellipsoids will have three components. X will be the component of the longest strain, and Z will be the component of the least strain. Like we have sigma 1, sigma 2, sigma 3 for the stress. Here for strain we have x, y, z. So x is the finest strain, which is the longest strain, and z is the finest strain, which is the shortest strain. That means any body which is spherical before deformation, that will get elongated along x, and that will get shortened along z. So if we see this ellipse, the long axis of this ellipse will be along the x, and the short axis will be along z, and y is the intermediate axis. So this is perpendicular to our plane along which this displacement has occurred. So displacement has occurred only in the xz plane. So if we see this particular plane, this is lying in the xz plane, and y is perpendicular to this plane. So in order to find the shear, we have to consider this lineation, and we have to take a section along this lineation. Then only we can identify the shear. Now if we consider any kind of ellipse here, we can see that the ellipse which are located in this particular plane, their long axis is like this, but as we go near to the center of this shear zone, we see that these ellipses are getting rotated, and here we can see that in the shear plane itself, this long axis of the ellipse are towards this direction. So this x, y, z axis is getting rotated here. So from the x, y, z axis, if we identify this x, y, z axis, we can find out which is the uh, shear plane here, and at what location we are from the plane. In this figure we can see that if we can understand the deformation of this foliation plane, we can find out what sense of shearing is taking place, and which is the boundary of the shear plane, and which is the center of the shear zone. Another interesting thing we have seen in the shear zone are the porphyroclasts. Like we have also seen that these porphyroclasts have some tails. Now from this porphyroclast, we can find out which are the direction of compression and which are the direction of elongation. Now if we see this porphyroclast, we can see that this light brown colored quadrants are the zones of compression, and the light pink colored quadrants are the zones of extension. Now in the compression zone, we have the two arrows towards each other, and in the extension zone we have the two arrows moving away from each other. So if we take the resultant here, so compression like this and extension is like this, so the resultant will be moving from here to the right hand side. So the resultant shear because of this deformation can be seen to be from the center towards the portion. If we similarly go to the bottom tail, left hand side tail, then we can see that the shear will be from the center part to the towards the tail. Then I easily identify the sense of shear from the porphyroclast. Now as the shearing gradually increases, as this movement along this shear gradually continues, this porphyroclast tends to get rotated. As it gets rotated, these tails tend to get dragged, and as this gets dragged, so we will see that at some point it will cross this central part, and it will come like a band here. This takes a S shape. So this way the deformation gradually continues, and from this deformed porphyroclast we can still identify what is the sense of shear. So suppose we have this initial porphyroclast, so we call it sigma porphyroclast. Now what happens in this porphyroclast, the minerals which form this porphyroclast like that gradually gets broken and recrystallized in the side, and this forms the tails. And from the tails we have understood that if we draw an arrow from the crystals to the tail part, then we will find out what is the direction of the shear. And slowly as this porphyroclast gets rotated, they will and this tail will get more and more rotated, and if it is getting pulled more beyond the center is here, so it's getting pulled up to here, so this is called a delta porphyroclast. Now in this delta porphyroclast also we can identify the sense of shear by knowing the sense of rotation. Similarly, we have some kinds of shears called sigmoid shears. So what is the difference between a sigmoid and a sigma porphyroclast? These sigmoids are not exactly porphyroclast. So they are like say this tail portion or some other mineral fragments which are totally fine grained. We do not have the nucleus of the remnant crystal here. Only fine grains are there. These fine grained crystals, they are getting broken from the original porphyroclast, or they have come from some other sources and they have got aligned like this porphyroclast. And from here also, if we draw a arrow from the center to the tail, then we can identify the sense of shear. So in these three kinds of rocks that we are describing from this porphyroclast, we can see a sense of textural shear here. So there are some kinds of porphyroclasts which are formed in a symmetric way due to recrystallization of some minerals in some say orthorhombic crystal system. So in such cases the porphyroclasts are not useful for CS because we do not know which direction is the movement from this kind of porphyroclast. So we have different kinds of porphyroclast in myelinites, and basically using this porphyroclast we can identify what is the sense of shear. Next we can see in this figure, we have already discussed this in case of granulation cleavage, that suppose we have some initial kind of one foliation, and after that there is a secondary foliation which got developed due to a shearing. As the secondary foliation develops, there will be an alignment of some minerals, like, and this will lead to formation of some secondary foliation planes which will be related to the shear. So this will be called the shear band, and this will be represented by the letter C. These are formed because the foliated fabric becomes unstable due to shearing. Moreover, what we see here is that the S surfaces, like the previous foliations, we are getting arranged in some parallel zones. The bands which differentiate these S surfaces into different zones, these are called the shear bands. To the increasing shear towards this side, the the C bands are becoming more closer. Likewise, suppose we have a set of deformations or different sets of shearing which have taken place on the rock. Then after this C shearing, we can get another kind of secondary plane of shears which are called C dash shear, because continuous deformation, the C and S fabric, they got parallelly aligned, and new shear plane called C dash shear plane has formed, and this C dash shear plane will be inclined to the sense of original sense of shear. So that is say around 15 to 25 degree, very gentle dipping direction from shear kind of foliation planes which are developed later are called extensional shear bands and denoted as C dash, and they are generally more discontinuous than the C planes. In field, it may be difficult to identify whether it is a C plane shear or a C dash plane shear. But one thing we can see here is that if we consider this C dash shear plane also, the sense of shear here will be in the same direction as in the C plane. So if it is a dextral shear here, so original shear also will be the dextral shear. One important thing to note here in identification of the sense of shear from the C plane is that this thing is occurring along the C plane. So this as fabrics, the original fabrics, they are getting dragged in some acute angle. So the sense of shear can be identified by drawing an arrow from the acute angle towards the exterior. So if we see that this is the acute angle, so if we draw an arrow from here to the outside, then we'll see that this is the sense of shear. Similarly here, the acute angle is formed in this direction, so if we draw an arrow from here, so we can get the sense of shear. Similarly for the C dash shear, we'll see some localized slip in the component of extension, so this will help us in estimation of the sense of shear here. Now that we understood how these foliations can help us in estimating the sense of shear in a shear zone, so next we will go to the thrust rates. So this foliation and lineation can give us some idea regarding the thrusting also. Let us consider a case here. In this figure A, we have some bedding here, sandstone, base of sandstone and shale. As the due to the development of the foliation, so we see that S1 foliation which are cutting across the bedding planes. After that, we consider a faulting or thrusting in this rock, and we see that this block has moved over this block. And if we see a section in this hinge region of the fold which is formed due to this thrusting, this is what we see is that there will be alternate bands of sandstone and shale, and this cleavage which are formed before deformation, they will show some kind of uh, refraction. This bending of the cleavage along these bands, these are called refraction. Now if we go to the incompetent layer like the shale, we see that the cleavage diverges, so they tend to move away from the center. And if we go to the sandstone, we see that the cleavage will converge, they will try to move towards the center. If we see the divergence of cleavage in the shale, it gives an indication of the shearing that is taking place, because normally in the shale, if we put it in a high pressure, then the foliation will be parallel to each other, but here they are diverging. So this means that these foliations are moving away in this side and they are moving closer towards this side, so they will give a sense of shear that is occurring along this shale. This also gives us an idea of the folding which is associated with this thrust belt. Okay, after this, we will see how this foliation and lineation can give us different information regarding folding in the region. Suppose let us consider this figure. So in this figure, we can see that we have different alternate bands. Say this, these are bands of sandstone and shale. So we have some kind of foliations which are developed due to folding. Now due to this, there are two sets of folding here. If we see the first here, we see that this rock is folded along this F1, so this is the axis of this F1 fold. Now this particular fold is not going in a straight line, rather it's itself is getting folded in some different axis, which is this F2 axis. So there is two sets of folding which are superimposed here. Now if we go into the different parts of this folders, so there we will see that suppose we go to the first this part near the core of this F1 fold. So what we see here is that we have this axial planar cleavage here. Now this axial planar cleavage, they are refracting at an angle at this boundary of this bedding planes from this sandstone to shale, because S0 is bedding here and S1 is our foliation, so they are at a higher angle to the bedding in the competent zone, and they are at a lower angle to the bedding in the incompetent zone. This is called the cleavage refraction. Similarly, we can see this cleavage refraction on both sides of the folding. Now after that, if we go into the middle portion, so here we will see that there will be another set of foliation which will be parallel to this F2 axial plane. So if we take a section, a small section from here, and if we see in minute detail, we will see that there are two kind of foliation here, S1 as well as S2. So S2 will be parallel to the axial planar of this. So from here we can identify, if we don't see this second fold, suppose this is a very big terrain and we are simply walking here, if we see these two kind of foliation, then we can identify that yes, there is a second folding also which is occurring in this place. Then after that, if we go towards the hinge of this fold, there we will again see the divergent and the convergent fans. The convergent fans will be seen in the competent rock, where these fans will converge towards the center. Similarly, in the incompetent rock, we will see the divergent fans. Now if we see a small portion from this left hand side of the rock, we can see that the bedding here is like this, and the foliation here is inclined in this way. So the acute angle of the foliation and the bedding is in the left hand side. So if the acute angle is in the left hand side, we can identify that we are standing somewhere in the right hand limb. Similarly, if we go to the left hand limb of this fold, we can see that the acute angle will move to the right hand side. So if we can identify which is the bedding and which is the S1 foliation, or if we can identify any kind of S2 foliation in the rock, we can get the entire folding patterns in the rocks in that region. This is a simple example of how this kind of folding is seen in some rocks in Chitradurga. So here we will have what is called a banded hematite formation. So here we will have iron bands which are highly compactly folded, and in this we will see some alternate bands of compact as well as incompetent rocks, and there will be refraction of cleavage in these competent and incompetent rock bands. So this cleavage refraction is shown in this right hand side figure. From this cleavage refraction and the set of cleavage, we can find out the number of folding episodes that have taken place, which side of the limbs we are standing. So suppose that we are standing in this limb, and this is extending for several kilometers. From this foliation we can identify which is the, whether it's the right hand limb or the left hand limb. These are the practical implication of foliation illumination, which is so useful in field in identifying the structural features. Similarly, sometimes we can see that there are some foliations which are inclined to the hinge or the axial plane of the folds. So if they are inclined to the axial planes of the folds, then we can identify that these cleavage planes are inclined to the folding. So we can identify that there is a separate set of deformations which are occurring in this place, which are oblique to this fold. This fold itself are related to some kind of compression. So there is a separate kinds of compression also which is occurring due to which this alignment of mica is along these previous planes. So this way the sets of deformations which are superimposed over each other can be visually identified from the foliation planes in the rocks. So today's lecture gave a brief understanding of the practical utility of this foliation and lineation, how they can help us to understand different kind of structural features and the taxonic deformation of the entire region. How simply knowing the alignment, the direction, or relationship of the foliations with the bedding, you can find out the entire deformational history of the place. So this I will conclude this talk, and I will always welcome any queries you have. So thank you.